distraction, fatigue, emotion. It's a pretty wild number, but according to the National Highway Traffic Safety Administration, human error causes a staggering 94% of all traffic accidents. Literally every single day. Our own biological limitations behind the wheel are costing lives.
And that sobering reality brings us to a huge, incredibly urgent question. As driverless technology quietly leaves the laboratory and merges right onto our city streets, can machines actually navigate our chaotic world safely without us?
Welcome to This Explainer. Today, we're taking an investigative, deep dive look into the race for the driverless future. We're going to strip away all that Silicon Valley marketing hype and look under the hood at the raw technology. We want to uncover exactly what it takes to replace the human brain with silicon and software.
Okay, part 1, defining true vehicle autonomy.
Let's cut through the buzzwords for a second. To really understand this, we rely on the SAE J3016 standard. Basically, it's the universal framework for automated vehicles, and it's divided up into 6 tiers. The lower half, levels 0 through 2, represent driver support, meaning the human is absolutely always in command. The upper half, levels 3 through 5, well, that's automated driving. By the time we actually reach level 5, the machine has absolute total control across all possible conditions. It's essentially an unlimited digital chauffeur. But here is the massive gap between promotional language and engineering reality. A lot of consumer systems out there today, even the ones capable of steering and braking on complex city streets, are strictly level 2. So legally and technically, you are driving. You are legally required to supervise that robot, and you have to be ready to take over in a split second if it makes a mistake. Moving right along to Section 2, how self-driving cars actually see. Under the hood, every self-driving car operates on a continuous, high-speed, 4-step loop. First up is perception, detecting the chaotic environment around it. Second is localization, pinpointing the vehicle's exact coordinates in the world. Third is path planning, using algorithmic foresight to chart a totally collision-free route. And finally, control, the actual physical actuation of the steering wheel and the brakes. The absolute foundation of that perception step relies on cameras. Just like our human eyes, they capture rich, high-resolution color, which is obviously essential for reading speed limits or checking traffic lights. But also, exactly like human eyes, they have a glaring biological weakness. They can be completely blinded by a setting sun, heavy rain, or thick fog. So to give the car superhuman vision, engineers use LiDAR. Instead of just taking flat images, LiDAR fires millions of invisible laser pulses in all directions every single second. By measuring the exact time it takes for each laser beam to bounce back, the car effectively feels the shape of the world down to the centimeter. It constructs a highly precise 3D ghost map, even in total darkness. Now, what happens when a massive blizzard blinds the cameras and confuses the lasers? The vehicle relies on radar. By bouncing radio waves off objects, radar completely ignores visual interference. It punches right through heavy rain, snow, and dense fog to accurately calculate the speed and distance of other vehicles. It acts as the ultimate rugged failsafe. Because every single one of those sensors has a physical vulnerability, the real magic happens through something called sensor fusion. The vehicle's onboard AI basically acts like an orchestra conductor, continuously merging data from the cameras, LiDAR, radar, and GPS. If the sun blinds the camera, radar steps in. If GPS drops out while you're in a tunnel, LiDAR maps the walls to hold the vehicle's exact position. In the driverless world, a diversity of sensors literally equals survival. The sheer computational power required to execute all of this is absolutely staggering. To run these deep learning neural networks and prevent collisions in real time, an autonomous vehicle generates and analyzes roughly 166 gigabytes of data every single hour. To put that into perspective for you, that is like downloading 50 high-definition movies simultaneously, all while cruising down the highway at 65 miles per hour. It's essentially a supercomputer rolling down the street.
All right, Section 3, the Great Industry Divide.
When it comes to actually building a true Level 5 robotaxi, the tech world is split right down the middle by a massive philosophical rivalry. On one side, you have Tesla, relying entirely on a vision-only system designed to scale globally overnight. And on the other side, you have Waymo, utilizing a heavily mapped sensor fusion approach packed with LiDAR, but restricted to meticulously geofenced cities. Tesla's bold, camera-only approach is rooted in a pretty simple philosophy. The road system is designed for eyes.
The argument here is that the entire global road network was built for biological humans using only optical vision and a neural network, our brain. Therefore, a digital neural network utilizing only cameras should be able to navigate anywhere, unconstrained by geographical limits, and without any of that expensive LiDAR hardware.
Conversely, Waymo refuses to rely on a single point of failure. Their whole engineering philosophy demands a physical shield of redundancy. If an unexpected whiteout snowstorm blinds the optical cameras, Waymo's system guarantees that overlapping LiDAR and radar can instantly take over. They maintain an active 3D map to guide the vehicle to safety. So they're essentially trading immediate global scaling for a localized ironclad safety guarantee.
Which brings us to Section 4, Safety, Liability, and the Law.
Here's the truth. Our physical engineering is vastly outpacing our legal frameworks. Right now, the United States relies on a pretty fractured regulatory patchwork. At the federal level, NHTSA governs the physical design and safety standards of the machine itself. But individual states, they're left to manage the chaotic reality of the roads, things like licensing, insurance, and accident fault. When the driver is actually just a piece of code, this division creates massive legal blind spots. A huge takeaway here is what happens as we move toward fully driverless robotaxis, those level 4 and 5 systems. The legal landscape violently shifts. In the event of a crash, liability moves away from the human in the car, who, at that point, is legally just a passenger, and it lands squarely on the shoulders of the software developers, the manufacturers, and the fleet operators.
And there are massive bureaucratic roadblocks to seeing these completely autonomous vehicles everywhere. Right now, to deploy a true Level 4 robotaxi without a traditional steering wheel or mirrors, manufacturers have to rely on federal exemptions. But there's a strict cap. They are limited to deploying just 2,500 of these futuristic pods per year, which is heavily bottlenecking the mass rollout of the entire driverless revolution.
So, as we wrap up this explainer, I want to leave you with a pretty wild thought. The artificial intelligence, the LiDAR, the sensor fusion, the raw engineering is advancing at lightning speed. It is moving way faster than our laws, our insurance policies, and maybe even our own cultural acceptance. We're standing on the brink of the biggest transportation revolution since the invention of the automobile itself. The machines are ready, but the ultimate question is, are we truly ready to share the road with them?